traffic? Me too. Well, hello everybody, and welcome back to Bowmath. How are y'all doing today? As you might have guessed, this video is going to be about traffic. And lately we've been discussing lowest common multiples, and in the previous video I showed you an application in Minecraft about how it can be used to basically determine how often two different things on different timers are going to sync up. And that was originally my plan for this video. I was going to go out, measure some traffic lights, and then look at how often they turn green, and then I can know how often those lights are going to sync up. And then I was going to connect that to an infamous local street in my city where people really hate this given intersection because of all of the different lights there. And I'm still going to do that. It's just we ended up not needing lowest common multiple for that. We ended up using a surprise little bit of math that we learned before, and I wasn't expecting it, but it's really cool. But before we get into that, let me just show you how we could use lowest common multiple in order to synchronize different lights. So let's say I have one traffic light here and another one over here. And I want to know how often they're both going to turn green at the same time. So just like with the Minecraft video we did, let's say this one, it turns green every 50 seconds. Alright, so the full cycle is 50 seconds, it turns green, then turns red, and then 50 seconds after it first turned green, it's going to be green again. And let's say this one turns green every 162 seconds, so it lasts a lot longer, but it's probably just a busier intersection. So the way we can figure out how often these sync up, well, every 50 seconds it's turning green, so 50 seconds, 100, 150, 200, right? Each time as we list off multiples of this 50, it's turning green again, right? And as we list off multiples of this 162, it's turning green again, right? 162, 324, 486, and so on and so forth. It's going to be turning green each time. So because each time it turns green, it's a multiple of these seconds, this ends up being a lowest common multiple problem. When is the multiples going to actually line up with each other? And it was the same logic for the previous application video we did. So the way to figure out when these lights are going to synchronize is we find the lowest common multiple of 50 and 162. And we do that by finding their prime factorizations. Alright, so these don't have a lot in common, which means that it's going to be a pretty large lowest common multiple. So we're going to have 2 times 3 times 3 times 3 times 3. That covers 162. And then we still need the 2 5s from 50. And so if you multiply this out or use a calculator or something, we're going to get 4050. So that's a really big lowest common multiple. So these aren't going to sync up very often. Only every 4050 seconds, these two lights are going to synchronize. Alright, so that's the idea, right? It's pretty much the same as the last video. We have two different timers and we just find their lowest common multiple. So you can now go out and measure some traffic lights, just time them and see how often they're going to synchronize with each other. And maybe if you're really good at planning and timing, maybe you go out at specific times when you know these are going to synchronize with each other, and that would give you an optimal drive. But now let's get into the local mystery. So I live in the city of Brandon, Manitoba, and one of the main streets in Brandon is called Victoria Street. And along Victoria, there's this segment of about 4 or 5 intersections that are all pretty close together. And the problem is with this intersection, locals always complain about how they can never get through it all at once. Even though they're really close together, they end up having to stop potentially multiple times along these intersections. And a lot of people just are really upset with it. They, send complaints to the city. They think it's really poor design and so on and so forth. And I looked online and I couldn't really find anything about the actual information about how long these timings last for these lights. So I decided to go with my buddy Kieran to downtown where these lights are, and we actually went to measure them. And I thought, hey, this is a great opportunity for lowest common multiple. Boy, was I wrong. So we're going to be looking at these 4 intersections here. The first one is this one here, and we are going to wait until, wait till the next one when it goes green. We are going to time how long it stays green for, how long it stays red for. We're going to do that a couple times just to make sure it's consistent, and then we're going to do that for each of the lights. And using that, we are going to figure out how frequently they sync up with each other. So let's get into it. All right, so we measured the first intersection and we found that the red light lasted for 35 seconds. The green light lasted for 45 seconds. And also, I'm just including the yellow light in the green light for simplicity because technically you're allowed to drive through while it's still yellow. And the period, that just means how often this whole thing repeats. So if it's red for 35 seconds, it's green for 45 seconds, an entire cycle is going to last for 35 plus 45 or 80 seconds. All right, so then we went ahead and measured intersection 2.
Okay, so here we are at the second intersection. We already got the results from the first one, and hopefully we'll see whether or not this is syncing up in some way.
In intersection 2, we found that red also lasted for 35 seconds, green lasted also for 45 seconds, and it had a period of 80 seconds. Interesting. So at this point, I was starting to get a little worried that we weren't going to be able to use lowest common multiples here, and I'm going to explain in a second, but see if you can figure out why lowest common multiples, like in the method I showed at the start of the video, probably aren't going to be so useful here.
Alright, we're at intersection 3. The first ones were pretty well the same period, so we're going to see if these are similar or not, and we'll get back to you.
The next light, lo and behold, was the exact same amount. Wow, alright, this was not looking too hot for us.
Alright, so this is the last intersection that we're going to be doing. So far, the last 3 intersections have synced up almost identically. All of them seem to have basically the same times. We're going to see if that pattern still holds for this intersection.
And the last intersection, thankfully, had 38 seconds and 42 seconds. So 42 seconds red, 38 seconds green. And I was thinking, okay, are we going to get to use some lowest common multiples? But once again, it had a period of 80 seconds, right? If you add those up, 42 plus 38, you still get 80. So why is it problematic that all of these have the same period? Well, the problem is that all of these intersections, if they have the same period, basically, they're always going to be doing the exact same thing, pretty much on the same timer. So if I measure any 80-second period, intersection 1, intersection 2, 3, and 4 will all be doing the same thing during those 80 seconds. And since all of these are kind of offset by each other, which we measured next, right? Like intersection 1, that doesn't turn green at the same time as intersection 2. They'll never turn green at the same time because they have the same period, right? Like if this turns green and this turns green 5 seconds later, then that means after 80 seconds, this is going to be green, this is going to be green 5 seconds later, and it's always going to be like that because they have the same period. So that means these are never going to synchronize. So I was thinking, okay, so we can't really use lowest common multiples to analyze this. So the next thing we did was we went out and measured how far apart are these intersections actually turning green.
Alright, so we've measured these 4 intersections. They have pretty well the same rate as each other. So now what we're going to do is look at how basically different they are, or how far offset they are from each other. So let's go ahead and do that.
Alright, so this is a topographical view of the street. Here are the 4 intersections we measured, and here is the timings that I've displayed in the chart. And we saw that, okay, when we started timing it, intersection 2 turned green first. So that was like our 0 point. And then 4 seconds after, intersection 1 turned green. So that means intersection 1 and 2, since they have the same period, are basically always going to be 4 seconds apart. So they're mostly going to be green or red at the same time. But then we found that, okay, 40 seconds after we started measuring intersection 2, intersection 3 turned green. And then 25 seconds later, intersection 4 turned green. So that's quite the difference. But still, we're seeing that since they're on this period of 80 seconds, they will always have this separation from each other. 4 seconds, 40 seconds, and 25 seconds. If we wanted, we could also go ahead and say, all right, if we're comparing it to intersection 2, intersection 4 happens 40 plus 25 or 65 seconds after intersection 2 turns, right? So we can do some adding and whatnot there. As we can see, lowest common multiple doesn't really help us because we have all of these same periods. But that's kind of the exciting thing about science, is that when you go and measure something, it's not always what you expect. Actually, it's often not what you were even hypothesizing, but you end up measuring something else and you get something that wasn't even necessarily expected. And that's where we get some really exciting things going on. So what wasn't expected here is the math that we needed for this wasn't lowest common multiple, it was number line sliding. That's right. We're flashing all the way back to like episode 1, 2 of this series. So we got light 1, 2, 3, and 4 right here. And I just have them all lined up. And as we can see for lights 1, 2, and 3, it's all the exact same because, well, at 0, they turn green. 45 seconds later, they turn red. 35 seconds later, they turn green. So that takes us from one full period, and that happens at 80. And then we go through another period, right? 45 seconds later, they're red. And 35 seconds later, they're green, and that's a second period, right? The second multiple of 80 is 160. And then for light 4, it was slightly different. So green for 38 seconds, and then it turns red, and then it's red for 42 seconds, and then back to green, and we continue like this. So all I've done here is I've just written out all of the information that we measured in terms of how long the green and red lights last for each of these intersections. But now what we're going to do is we want to basically see, okay, how offset are these from each other? How different are they going to be? Well, that's what these 4, 40, and 25 seconds is. And we can use number line sliding to do this. We know that light 1 turns green 4 seconds after light 2 was green. So that means we can take this number line and slide it 4 to the right, or we're adding 4 to the number line, right? So now we see that this 0 here is basically going to be lined up with 4. All right, awesome. So now everything has been slid over, right? So this turns red, and then 4 seconds later, light 1 turns red. And then after light 2 turns green, 4 seconds later, light 1 turns green. So they're always going to be offset by 4 seconds. So what does that mean? Well, in terms of just lights 1 and 2, if you get a red light at light 1, chances are you're going to be able to just go through both of them after because, well, light 1 turns green pretty much around the same time as light 2 turns green. So you're only going to be having to wait at one of these lights at most, and then you'll be able to get through both of them, usually. Now if we factor light 3 into this, it's 40 seconds after light 2. So that means I'm going to be adding 40 to this number line and sliding it down to right about there. So now 0, that lines up with 40. And we see, all right, things are pretty different now, right? Well, intersection 1 and 2 have red lights. Light 3 is usually green. And when intersections 1 and 2 have green lights, light 3 is usually red, right? So we see that, okay, that could become problematic. And let's also consider light 4. So light 4 is 25 seconds after light 3. So if we line it up at light 3 and then add 25 to it, that'll take us over here. And we also see that this 0 will line up with 65 with light 2, which we saw that 40 plus 25 was 65. So it still lines up with everything properly. But now we kind of see why these lights could be problematic. Because first of all, how often are they all green at the same time? Well, this one is green here at 80, which is 84, and then that'll be lined up with 44, which will be lined up with 19, right? So it looks like it's only green at this period of time. Anything before, it's going to be red in here, or anything after, it's going to be red in here or in here. So it's just this little strip in here where it's actually all green. But that little strip, because it lines up with 44 here and then becomes red immediately after, it's only 1 second. So that means for only 1 second are all of these lights actually green. And then we're going to get either some green or some red. And we see that, okay, let's say you get through and you have to stop at light 1 or light 2, right? The red. And then, okay, great, they turn green. But as soon as they turn green, you're pretty much guaranteed red lights over here at light number 3, right? And so that's part of the reason why people think these suck so much is because you have to stop at light 1 and light 2, and then eventually you're going to have to stop at light 3 and light 4. It's pretty much guaranteed because they turn green almost immediately before lights 3 and 4 turn red. And so we can use these number lines. It's really useful to kind of just get a visual representation of kind of as time goes on, when are they all green, when are they all red, and be able to really see what the problem is. And let's say you're going the other direction as well, right? And you have to stop at light 4, let's say, because it's red. And then it turns green. And let's say traffic's a little backed up. It's not long after till it's red. And even if you do get through, these are still red, right? So again, it kind of works in both directions, where we're seeing that if you stop at a red light, you're most likely going to be having to stop at 2 red lights in this first cluster and in this second cluster, because the greens and the reds pretty much kind of line up in opposite with each other. So I hope you found this video useful. I think it's a really interesting application of not just lowest common multiples in kind of the theoretical case we were talking about, but in terms of how multiples being offset from each other actually end up meaning that no synchronization happens, and then furthermore, that we can still get useful information by going back to number line sliding and seeing that this was actually quite applicable when it came to really getting a nice visualization of what's going on. So, while I'm not really able to give you any useful tips for driving down this street, at the very least we can kind of know the mathematics about why locals hate this street so darn much. Well guys, I hope you found that video interesting, and you know, maybe you want to get a little funky and go out into your streets and measure your traffic lights. Of course, be safe out there, and shout out to my boy Kieran for helping out. Go check out his channel at Vape Memes 2020 for only the spiciest videos. And yeah, thanks for watching, have a good one, stay groovy, and I'll see you in that next video.